Welcome back for part 3 of solving a first-order homogeneous differential equation written in standard form. Let's go and take a look at our third example. We want to determine if the given differential equation is homogeneous, and then if it is, we want to solve it. We should remember from the previous videos, we can show this is homogeneous if we can show the right side is a function of y divided by x, given by our notes here below. So we want to show the right side can be written as a function of y divided by x. So if we look at the numerator, notice how we have this y here. If we want this to be a function of y divided by x, we'd have to multiply this by 1 over x. So we can multiply the numerator by 1 over x as long as we do the same to the denominator. Now let's go ahead and multiply and see what we have. Our numerator would be y divided by x, which is good. And now we need to be careful with the denominator. We're going to distribute, so we'd first have x over x plus we'd have 1 over x times the square root of xy. If we were to bring this fraction underneath the square root, it would have to be 1 over x squared. So this is going to be equal to the square root of xy divided by x squared. Remember, if we have x, we can write this as the square root of x squared. However, written like this, we would have to assume that x is positive. So we can write this as the square root of xy divided by x squared. Let's go ahead and simplify the denominator. Well, x over x simplifies to 1, plus here one factor of x would simplify out, leaving us with the square root of y divided by x, which is good news. Notice how wherever a variable appears, it's written as y divided by x. Therefore, this is a function of y divided by x, and therefore this is a homogeneous differential equation. So now that we know that it's homogeneous, we can solve this by performing the substitution v equals y divided by x. And if we solve this for y, we'd have y equals x times v. We need this because we need to find dy dx. So by applying implicit differentiation in the product rule, we can show dy dx equals x times dv dx plus v. So now we'll perform substitution using these two equations. So again, dy dx is x times dv dx plus v. And the right side is now going to be, this will be v divided by 1 plus the square root of v, which I'm going to write as v to the 1/2. And now we need to solve this differential equation using separation of variables. So for the first step, we'll subtract v on both sides. I'm going to write this as minus v over 1, because to combine these we have to have a common denominator, and this would be our common denominator. So I'm going to multiply this fraction by 1 plus v to the 1/2 all over 1 plus v to the 1/2. Now that we have a common denominator we can subtract, our denominator is going to stay 1 plus v to the 1/2. Now looking at the numerator, notice how we'd have a v here, and then a minus v when we distribute, so the v terms simplify out. Then we have a negative v to the first times v to the 1/2. Adding the exponents, we would have negative v to the 3/2. Now again, we want to solve this using separation of variables. So we want the x terms and dx on one side, and the v terms and dv on the other. So for this next step, we're going to multiply both sides by the reciprocal of x, or 1 over x, and also multiply both sides by the reciprocal of this fraction. That would give us 1 plus v to the 1/2 all over negative v to the 3/2 dv dx equals 1 over x. And now we'll go ahead and write this in differential form, or we can think of multiplying both sides of the equation by dx, which would give us this. Now that we have the v's and dv's on one side and the x's and dx on the other, we have separated the variables, but before we integrate, let's perform some algebra on this fraction here. We can rewrite this as 1 divided by negative v to the 3/2 minus v to the 1/2 divided by v to the 3/2. Simplifying here, we'd have negative v to the negative 3/2. And then here we'd have minus, subtracting the exponents, we'd have v to the 1/2 minus 3/2, or v to the negative 1 power, which we can write as minus 1 over v. And now we can integrate both sides of the equation. Now applying the power rule here, we'd add 1 to the exponent and then divide by the new exponent. So that'd be negative v to the negative 1/2 divided by negative 1/2, or times negative 2. So this is going to be 2v to the negative 1/2 minus natural log absolute value of v. We would have a constant of integration, but we'd also have one on the other side. So let's just put it on one side. This is going to be equal to natural log absolute value of x plus c. Now remember, we want our solution in terms of x and y, so now we're going to replace v with y divided by x. So we'd have 2 times, now because this exponent is negative, y divided by x to the negative 1/2 is the same as x divided by y to the positive 1/2 minus natural log absolute value of y divided by x equals natural log absolute value of x plus c. Let's use our property of logarithms and expand this. So we'd have minus, then we'd have the quantity natural log absolute value of y minus natural log absolute value of x equals natural log absolute value of x plus c. The reason that's helpful is, notice how this would be a positive natural log x on the left as well as on the right, so these two simplify out, leaving us with 2. I'm going to go ahead and write this as the square root of x divided by y minus natural log absolute value of y must equal a constant c. This would be the general solution to our first order homogeneous differential equation. Let's go ahead and finish by taking a look at this graphically. What I mean by that is we can generate the red slope field by using the original differential equation, and then given our general solution, if we select the following values of c, 0, 0.5, 1, and 2, we can show 4 possible solutions from the family of solutions below. Each function below represents one possible solution from the family of solutions. Okay, I hope you found this example helpful.